In this question, we're going to consider the following closed loop transfer function. So 2 over s cubed plus s squared plus 3s plus 8. So there's two parts of this question. Part 1, write down the characteristic equation. And part 2, use the Routh-Hurwitz stability criterion to determine if the system is stable. So for the first part, nice and straightforward, we effectively just take the numerator of the closed loop, the denominator of the closed loop transfer function, which is s cubed plus s squared plus 3s plus 8, and equal that to 0. The next part, so use the Routh-Hurwitz stability criterion to determine if the system is stable. What we need to do is we need to populate the Routh array. So I'm just going to start putting this together. And because it's of a third order, we end up with this amount of rows. And then to populate the Routh array, this ends up being A3, this A subscript 2, A subscript 1, and A subscript 0. And we effectively get these values from this characteristic equation here. So A3 is just its lead coefficient, which is 1. A2 again is that one there, which is 1. A1 is 3. And A0 is 8. These two numbers here end up being 0. And then what we have then is the need to determine B1. And I'll show you B2 and also C1. So to determine B1, we use the following equation. So B1 is equal to 1 over AN minus 1, and then the determinant of AN, well, there's 2 by 2, AN minus 2, AN minus 1, and AN minus 3, which in our case N is obviously third order, so we end up with just that being there at 2. Oh, sorry, I've missed a minus there, don't forget the minus. Here, AN3, AN2, AN1, and AN0. So if we populate this, because you're probably noticing this 2 by 2 here is just a 2 by 2 here, and this term here, known as the pivotal element, is effectively just that A2 there, which is a value of 1. So if we put the values in, minus 1, and then 1, 1, 3, and 8, then undertake the calculation, so 1 over minus 1, and then if we take the determinant, which is just going to be 1 multiplied by 3, take away 1 multiplied by 8, excuse me, it's been a long day, 1 multiplied by 8, take away 1 multiplied by 3, then all brackets, and then put the whole thing in brackets. And then if we work that out, it's going to give us effectively 3 take away 8, which is going to give us 5. So it's going to give us 5 over minus 1, which is going to give us a value of minus 5. Right, so then we've worked out B1, so that's B1. So we go back up to the table. We can put in here, this is equal to minus 5. And if you were to work out B2, you would determine that is 0, and that's always the case, that's 0. And C1, that C1 always ends up being equal to A0, determines an A0, so a value of 8. So in the undertaking the Routh-Hurwitz stability criterion, we're interested in looking down at this pivotal column here, and what we're doing is we're using this table effectively to evaluate any sign changes along this column. The number of sign changes equals the number of poles that are in the right half of the S-plane. So in this case, if we go down here, so we've got 1, so it's positive, 1 positive, minus 5 negative, so we've got 1 sign change. And then back to 8, so that's another sign change because we're going from negative to positive, so we've got 2 sign changes. So what we know is we have effectively, therefore, 2 sign changes, therefore 2 poles, which are the roots of obviously the denominator in the don't know, excuse my pen, therefore 2 poles in the right half of the S-plane, and hence you've got two poles in the unstable region. So there's unstable region, therefore this closed loop control system is unstable. Okay, it's an unstable closed loop control system. So we've undertaken the Routh-Hurwitz stability criterion, this test, quick test, to enable us to determine that we've got two poles in the right half of the S-plane.